All right, so then I guess we can start. So welcome to this mini symposium on nonlinear PDEs in neuroscience. Our first speaker is Delphine Sadlor from Sorbonne Université. You can go ahead and share your slides as soon as, if you're allowed to, I guess. Delphine?
Yes, I just searched my slides. Sorry, I don't know why I didn't find it.
Okay, just take your time. So I'll just remind all of you speakers that you have 25 minutes in total. So as soon as you're ready, Delphine, you can just
okay, I found it.
Begin.
Okay.
Yeah.
So.
And I know your topic is going to be some PDE models in neuroscience, right?
Okay, do you see? No?
You see, but you can probably go full screen as well.
Yes, donc fichier, présentation, like this.
Okay, perfect. Thank you.
Okay.
The floor is yours.
Okay, so I thank very much the organizer for the invitation, and I'm very happy to give a talk here. So my talk is about qualitative analysis on a PDE model of neural networks. So the aim of this talk is to make an overview of several results that was obtained the past years around this the models that we have studied with several collaborators. And so the general problematic is, so here we consider an homogeneous model, and we want to understand how appear complex patterns in neural networks and how they can emerge from individual neurons. So all these complex patterns can be related to several aspects, as for example, the intrinsic dynamic of the neuron, memory effect, refractory period, or, for example, delay of transmission. And to give some answer on this question, in this talk, I consider a model which is where the neurons are described via their membrane potential. So here, just a quick recall of the dynamic of a neuron with respect to its membrane voltage. When there is at the resting state, so the potential is here at minus 70, and either spontaneously or if there is a stimulus, the membrane voltage can suddenly increase to reach a certain value that we call a action potential or potential voltage, action potential. And at this time, the neuron spike, and it comes back with these dynamics to its resting potential. So to describe precisely this dynamic, we have to use several complex processes as opening and closing various channels, for example, as Hutchinson type models. But here we simply use that we call intermediate inferior model. That is that when the neuron discharge, instantaneously, we assume that the membrane voltage comes back to its resting value that we will call after VR. So if here I present the equation, so it's an equation which, as I said, is studied now from many years. And it was originally proposed by Brunel and Hakim. So the solution here models the potential of membrane at time t and with a membrane potential V. And the membrane potential V is assumed to belong to -infinity Vf, where Vf is the value of the action potential, that is when the neuron spike, and Vr here is the value of the reset potential, that is when the values that take the neurons when they discharge. So in the equation, we see several terms. So there is a red term here, which is n of t, which describes the flux of neurons with discharge at time t. And this quantity is computed via the derivative of the function p at the boundary Vf. Okay, so, and there is a Dirichlet boundary condition. So we assume that the neurons with potential Vf is always equal to 0. Okay, so with this, in particular, we have, at least formally, mass conservation of the solution, which is normal. There is another term. So this is a term which will give the coupling between the neurons, which is here, Bx of t. So B is a constant, it's a parameter which can be positive or negative or equal to 0. And x of t models the amplitude of stimulation that receives the network at time t. Okay, so here in the equation, it's the equation of Dirichlet with a diffusion due to the noise. The neuron with discharge, so come back to a value VR, and there is a drift term, which is given by the integrate and Fourier model. And j'arrive pas à faire. Okay, sorry. Sorry, when I want to switch, cannot do it. Sorry, I cannot switch my. Okay. 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 So all the dynamic and finally is given by x of t, and there is several choice for x. So there is okay, infinitely many, but in this talk we are consider two of them. So the first is x of t equal n of t, because originally the mathematician have studied this case. And we will say that in this case, if you want to observe the qualitative dynamic, there is no many possibility. Okay, it's okay. There is no many things happen, at least numerically. So we can ask what happens if we add a delay transmission, and because biologically the transmission is not instantaneous, and there is a delay transmission. So first, if we simply consider the case, or simply consider the natural case x of t equal n of t, the equation is this one. So it's the same as before, except that I replace x by n. And here, the first question that we can ask is, before study the qualitative property, is the problem is well posed. And this question was studied by many authors that I mentioned here. And essentially what happens, so I put a draw here. So here it's a parameter B, and I explain what happened with respect to the parameter B. So when B is negative, it's an inhibitory case. So this means that the drift given by the interaction push the neuron from to -infinity, to the left. Okay, and in this case, the equation is always well posed. However, as soon B is strictly positive, Bn of t, the drift given by the interaction, goes through Vf, and I recall that the flux of neuron is given by the derivative, so we can expect that the derivative becomes larger and larger. And in this case, if you assume that the initial data is enough concentrated near Vf, so I make a little draw here, then we have blowup. But if the initial data is not concentrated too much in your graph, it's okay. And for B large enough, there is always blowup. Okay, so it's for the existence and uniqueness. Now, if we are interested of the qualitative dynamic, if you make numerical simulation, we have only two types of dynamic. Either we have convergence to a stationary state, so it is given by here. So here we have an initial data to represent the solution at different time, and we see that very quickly the solution converges to a stationary state. And the second type of dynamic is blowup. So this means that the solution is not well defined globally. So here we have an initial data, and this time we see that the solution here is such that the derivative at VF, so here VF equal 2, gets larger and larger, and finally we do not have okay, the stem is not well posed. Okay, so we are not very happy because we wanted to, in particular, to have a periodic solution, and we do not see this. This does not mean that they do not exist. This means that numerically, to my knowledge, nobody has found a periodic solution. However, we can nevertheless try to theoretically understand what happened asymptotically. So can we describe theoretically what we observe numerically in this context? So this is what we have done. And okay, so before this, I just explain what we say, so that we have done. So before explaining, I just explain what are the stationary states. So we see that we here have an implicit formula. And essentially, the results is that if B is small enough, so it's in the green part, we have a unique stationary state. There is a blue area where we know that there is at least one stationary state. Sometimes we know that there is more than one stationary state. And for B large enough, there is no stationary state. And what we have, what we can prove that we can prove theoretically that in some cases we have convergence to the stationary state. So that we can prove that the numerical observations are effectively true, in fact. However, we have to separate the inhibitory and excitatory case. And in the inhibitory case, we have a global attractor. So what does I mean by global attractor? This means that if the interconnection is small enough, so we only know what happened for low interconnection, because when the interconnections are big, it's too big, the equation is much more complicated. So when B is small enough, whatever the initial data, essentially, we have convergence to a stationary state. Okay, but in the excitatory case, the result cannot be true, because when B, whatever the value of B, which is positive, we can have blowup. So in this case, we can only prove that we have exponential convergence to stationary state, assuming that the initial data is close enough to the stationary state, and by taking B small enough with respect to the initial data. So the difference between the initial data and the stationary state. And so the existence of periodic solution, as I said, there is not numerically observed. Okay, so if I make a draw which explains just what I told here with respect to the value B, if in the green part, so B negative and not too large, we know that we have a global attractor. If B becomes large enough, numerically we observe that we have a fast convergence to a stationary state, but we don't know how to prove it. So it's an open problem. And the difficulty is essentially due to the fact that when B is large enough, we deal with strong nonlinearity, which is not the case when B is smaller. Okay, for positive and B not too large, we have convergence depending on the initial data. And if B is large enough, as we even do not have stationary state, so we cannot have convergence to stationary state. Okay, so by choosing x of t equal n of t, we are not very happy because it depends on what we search, but if we want to search a periodic solution, we are not very happy. So we say, okay, it's not a problem. Let us integrate in the model the fact that the neurons, that there is a delay between the signal that receives the neuron and the fact that they integrate it. So we model it by the fact that here we have a parameter d, which is strictly positive. So if we do this, the question of global and existence of the solution is not anymore a problem. Okay. So it was studied also by many authors. And if we're interested of periodic solution, and and we say, okay, let's see what happened in the excitatory case. And numerically, it is what we observe. We observe that either we converge to a stationary state, either we observe oscillation. But if we look more closely to the oscillation, what we observe, so here it's the time t, and here it represents n of t, that is the total, the flux of neuron with discharge. So we see a certain periodicity here because the length between the two large spikes seems to be the same. However, we see that n of t during the time gets bigger and bigger. And so we observe numerically that we do not have convergence to a stationary state. That we do not have periodic solution, but we have some regular oscillation which become larger and larger and goes to plus infinity. So in fact, this situation is quite normal because if you expect a periodic solution in some kind, there is oscillation. This means that there is oscillation around a stationary state. However, so this simulation was made for B large enough. If we look at the stationary state of this equation or the stationary state for the equation without delay, they are the same. So this means that for B large enough, there is no stationary state. Okay. So, but the solution is globally well defined. So we know that for B large enough, we will never have convergence to stationary states simply because the stationary states do not exist. And this means also that we cannot have oscillation between this stationary states which do not exist. So it is not a proof, but it is a way to intuitively explain here what happened. So okay, so in the excitatory case, we still do not have periodic solution. We have this kind of pattern when the activity of the neuron gets bigger and bigger, and an infinity goes to plus infinity. And okay, we say let us see what happened in the inhibitory case. So I recall that without delay, we have no periodic solution, a priori, at least numerically, and we have even observed that it converges very fast to a stationary state. However, if we add some delay, we observe interesting patterns. So I just put here. Do you see the? You see the? No. Okay. I have to switch. Okay. Voilà. Okay, so here it's a simulation of the solution for B equal, I don't remember exactly, maybe minus 50. Okay, so B negative and B large. And let us see what we observe. Okay, so here, what you observe, at least visually, it seems very simple. We observe a function. So here, on this, which is represented is the solution P of TV. So if we look this, what we observe is simply something which looks like a Gaussian, which goes from the left to the right. And if we look attentively, I don't know if you see this go faster from the left than from the right. I don't know if it is clear. Oh, the first, okay, just put it. For the first, it is clear, but after it's less clear. Okay. Okay, so we have observed this numerically, and we say, okay, it seems to be simply a Gaussian with a wave which tells us that we go from the left to the right. Maybe there is a possibility to describe it theoretically, because it seems quite simple, at least. Alors pourquoi je vois pas? Ah voilà. At least visually. Okay. So to study this, to try to tackle this theoretically, to do not have too many notation, we have chosen the potential action potential equal to 0 and the DD equal to 1. Okay. So the problem here is that we still have a quite complex PDE, and we have tried to understand what happened for B very, very small, so B very, very negative. And to this, we have said, okay, numerically, we observe that the dynamic is governed by a Gaussian with a speed wave, which may depend on time. Okay, let us write the solution as a wave with a remainder time. Okay, where phi is like this, and C of t is the speed, the velocity, which go from the left to the right. And so what we have proved, so this part is not very difficult, we have proved that the remainder time is well controlled by the flux of neuron with discharge. So as we expect that for B, very, very small, n goes to 0, okay, the remainder term is small. So now if you want to control the dynamic of P, we have to determine what is C. The problem is that C, if we look at the equation of C, we do not have a closed equation. And we want to have a closed equation. And to this, what we have done, so this is this part which is a heuristic. We have said, okay, assume that R goes very fast to 0 when B goes to minus infinity. If it is the case, then approximatively C of t will satisfy this closed equation. So this means that we have reduced our PDE, at least asymptotically, to a delay equation of C. Okay. And so the question which remains is there periodic solution of this equation? So is there periodic solution? And as we look at the asymptotic, do we have, when B goes to minus infinity, for example, C, which goes to a constant, which will be not good, because we want to obtain a periodic solution. If the limit when B goes to minus infinity goes to a constant, this will mean that when B goes to minus infinity, at the limit, we do not have periodic solution. So to study this equation, and we have make a general theorem to prove a periodic solution. And more precisely, we have construct an explicit asymptotic profile of this solution when B goes to plus infinity to precisely describe the dynamic asymptotically. And so I did not, I did not explain how we did it, but essentially, what we have observed, that the solution was projected very fast from the left at a distance of the size b power alpha, and come back on an exponential peak, but much slower than on the left part, on a time period like ln minus b. So this means that the period of the solution is like ln minus b. And okay, so to finish, I just put a numerical simulation of the profile C of t, which gives the dynamics. So we see what happened. Huh? So here it is a case where we come back to the right, and we rapidly goes back to the left and come back again and again. And we see, so it is the different value of b. So b equal minus 50 to b equal minus 5,000. Okay, so the conclusion, we have obtained some theoretical results which well describe, in fact, the numerical simulation that we have observed, but at the cost of a conjecture that this remainder term goes very fast to 0, and this question we do not know if it is true or not. We hoped that it is true. Numerically, it seems. Okay, so I thank you. I thank you very much.
Thank you, Delphine, for a very nice talk. I think to keep the time, we have to skip questions, but feel free to ask questions in the chat, and I guess Delphine can answer them, right? Yes. So then we go on to our next speaker, which is Xuan Du from Peking University. Are you here, Xuan?
I need to share the screen.
Yes, you do.
So maybe that could stop sharing.
Yes.
Yeah.
Thanks.
Ah oui, sorry. Voilà.
Oh, okay. Thanks for the invitation, and also thanks, Stephen, for introducing the NLF model in the previous talk. I'm very happy to share our recent work here, and we propose a generalized solution for the NLF model. And this is a joint work with my supervisor, Zhenan Zhou. So let me introduce the problem. To model a large number of spiking neurons, we can consider a mean field model in which the neural network is described by two quantities, a probability density P, which gives the wattage distribution, and the fan rate N, which gives the spiking activity. The meaning of the N of T is the number of spikes per unit time. And remarkably, as mentioned by Delphine, the fan rate N of T can blow up. As in this figure, the fan rate N of T diverges to infinity in finite time. And mathematically, this means you cannot have a global classical solution because the classical solution stops when the fan rate blow up. And this is not just a mathematical issue because the blow up of the fan rate corresponds to the synchronization of a neural network, which in this context means the fraction of neurons spike at the very same time. So if we want to describe the synchronization in this mean field model, we need to answer this question: what happens after a blow up of the fan rate? And to answer this question, in this work, we propose a generalized solution from a new perspective and prove its global well-posedness. So precisely, we also consider the NLF model in which each neuron is described by its wattage or member potential. And the evolution of the wattage is subject to the leaky effect and a noisy external input. And when the wattage reaches a threshold VF, it's the neuron spikes, and the voltage is instantly reset at a lower value VR, and the spike will influence other neurons. Here is a typical trajectory of a voltage of a neuron. And in the mean field limit, we can derive the following nonlinear PDE for the probability density P and the fan rate N. In the advection term, the first term minus V denotes the leaky effect, and the second term describe how one spike influence other neurons. Just like in Daphne's talk, if B is positive, we are in the excitatory regime, and the negative B represents the inhibitory regime. The diffusion coefficient also consists of two terms. If the first term A0 is positive, it denotes the external noise from the input. And the second term is the intrinsic noise, which is the noise due to the spiking activity we see in this neural network. And we have this parameter A1 non-negative. In analyze in many literature, this A1 is often set to be 0. And when a neuron spike, when the neuron's voltage reaches VF, it spikes and it is instantly reset to VR. So we have a Dirichlet boundary condition at VF and the Dirac source term at VR. And the neurons reset at VR are exactly those who hits VF and the spike. So the coefficient here is the fan rate N of T, and the fan rate N of T is determined by the boundary flux at VF. Since the diffusion coefficient also depends on the N of T, so this equality actually gives a self-consistent equation for the fan rate. And for such a model, the fan rate can blow up in finite time. And mathematically, you cannot continue a classical solution beyond the blow up time. And indeed, as long as the fan rate does not blow up, it has been proved that the fan rate will remain finite. As long as the fan rate does not blow up, it is proved that you can continue the classical solution. So the blow up of the fan rate is exactly the obstacle which stops a classical solution. However, it does not mean the underlying physical process or the neural network also stop when the fan rate blow up. On the contrary, it means the blow up of the fan rate means the neural network synchronized, like 10% of the whole neural network spike at the very same time. This also relates to the multi-finite event, which is a recent concept in computational neuroscience. So to describe synchronization in the mean field model, we need to go beyond classical description and consider generalized solutions. And let me first give a brief review around the blow up for this nonlinear equation. And the nonlinearity comes from two parameters, the B and A1. For this, as long as B is positive or we are in the excitatory regime, the solution can blow up. And nevertheless, we can still have the existence of we can still have a global classical solution in the excitatory regime if we impose some conditions both on the parameter B and on the initial data. And on the other hand, if B is negative, we can also always have a global classical solution. However, most analysis literature for this equation focused on the case A1 is 0, including this existing result. Indeed, if A1 is positive, then no matter B is positive or negative, there always exists smooth initial data that leads to the blow up. And intuitively, we can write the fan rate as a function of the boundary derivative from its definition. And we can say to have a finite and non-negative fan rate, we need this constraint. And if A1 is positive, this constraint will implies a finite upper bound of the boundary derivative, which is difficult to satisfy. For generalized solution, the pioneering work is this paper in 2015. They proposed a generalized solution based on the corresponding Minkine-Vilasov type SDE rather than this Fokker-Planck PDE. And in their definition, they make a clear link between the blow-up of the fan rate and the synchronization of a neural network. They also prove the global existence of their generalized solution, yet they also only work with the case A1 is 0. And in this work, we propose a generalized solution from a new perspective. And in particular, our construction is only based on the PDE and work with the case A1 positive. So to summarize, with both mathematical motivation to have a global solution and the scientific motivation to describe the synchronization in the mean field model, in this work, we propose a generalized solution which allows the blow up of the fan rate and prove its global well-postedness. So the idea of our generalized solution is based on introducing a new time scale tau. We call it a dilated time scale. It is given by this change of variable formula, and it's related to the fan rate n. We can formally derive an equation in the new time scale tau, which I will show in details later. But the main points here are that the equation in tau, the blow up of the fan rate is allowed, and moreover, we can show that the equation in tau is globally well posed in the classical science. So now we have a classical solution in tau, and we want to define generalized solution in the original time scale t. To do so, we want to change back from the time scale tau to time scale t. And we want to find the change back map tau of t. And once this change back map is founded, we can define the generalized solution as time t to be the classical solution as time tau of t in the new time scale. However, this map is not trivial because tau of t can be discontinuous when the fan rates blow up. Tau of t can has a jump, and by the construction, the jump of tau of t will lead to a jump in time of our generalized solution when the fan rates blow up. So when the fan rates blow up, the density function of our generalized solution will have a jump in time. And this jump in time essentially contains how we resolve the blow up issue in our generalized solution. So let me explain more about this. We define the time scale tau where this change of variable from time scale t. But now we are in the time scale tau. We want to change back to t. So we invert this formula, and we want to define the map tau of t. But what we can directly define is the map t of tau by this integral, and tau of t shall be an inverse of this t of tau. However, t of tau may not be a strictly increasing function. Suppose in the dilated time scale tau, the fan rates blow up on a whole interval, then it means 1 over n plus 1 is always 0 on the interval tau 1, tau 2, which implies the function t of tau is flat on this interval, and all tau in that interval will be mapped to a single t star in the original time scale. So we choose tau of t to be the right continuous generalized inverse of t of tau. And it will have a jump at the blow up time t star. To summarize, in the time scale tau, the blow up of fan rate happens on an interval, but in time scale t, the fan rate just blow up at a single time point. And the whole interval is compressed to a single time point, which leads to the map tau of t has a jump. that point. And since our construction for generalized solution is to assign the solution in tau, solution in as tau of t to be the generalized solution as t. So the jump in the scalar map tau of t will lead to a jump in the density function p. And we can say in the original time scale, when the fan rays blow up, the density function will have a jump in time at the blow up time t star. However, in the dilated time scale tau, the jump time t star is dilated to an interval tau 1, tau 2, and the jump at t star is dilated to a continuous dynamics in that interval. And let's watch a movie about this. So when the fan rays does not blow up, both the t time scale and the tau time scale are evolving. And when the fan rays blow up, the t clock stop, but the solution is still evolving in the tau time scale. And when the solution gets rid of the blow up regime and the t time scale resumes to evolve. So we say the fan rays blow up in an interval in the tau time scale, and this is compressed to a point in the t time scale, and which leads to a jump in the density function before and after blow up in the t time scale. And let me explain more on the derivation for the equation in tau. So we recall the original equation in t. We do a reformulation in the reset term. We just substitute the definition of n of t into the reset term. And then we work with this reformulation. Since our generalized solution is defined by, since the time scale tau is defined by this change of variable, we just divide everything by n+1 in the new time scale. Just divide everything by n+1 for the equation in t. And then the time derivative in t will become the time derivative in tau. And we use the p tilde for the new density function in tau. And here, these coefficients are just divided by n+1, and we introduce the notation n tilde to write them. And here, the ellipsis just means this coefficient is the same as the diffusion coefficient. So we can derive the equation in tau, and here the nonlinearity is in n tilde, which can be written as an explicit function of the boundary derivative. But here we just need to know that the blow up of the fan rate is equivalent to that n tilde is 0. However, n tilde becomes 0 is allowed in the equation in tau. Therefore, we say that the blow up of the fan rate will not hinder the evolution of the density function in the new time scale. Moreover, we can prove that the equation in tau is indeed globally well posed in the classical science. This is still a nonlinear equation because n tilde depends on the solution. However, this nonlinearity is always bounded. It's between 0 and 1 by its construction. So this is an advantage for global existence. And another point is, since n tilde is between 0 and 1, this diffusion coefficient is between A0 and A1, which are two positive numbers. So we have uniform parabolic, so the equation is uniformly parabolic. And here we rely crucially on that A1 is positive. In the proof, we adopt the framework for the classical solution for the equation in T in this paper. So we can have a global solution in tau, and by this change of variable, the lifespan of the solution in T is given by this infinite interval, and the global hypothesis in the original time scale T is equivalent to that to show this T star is infinity. This is that's not necessarily true, and it relates to the long time behavior in tau. And our main analysis result is to study the global hypothesis in T, and there is a crucial value VF minus VR for the connectivity parameter B. So if B is less than this value, we can always have global solutions. This including the case B is negative, and also the case B is positive but lower than VF minus VR. On the other hand, if B is greater than this crucial value, we can have initial data which leads to T star equals to 0. And by this definition, we can say T star is 0 is equivalent to that N is always infinity in the dilated time scale. And we call this case an internal blow up. So let me discuss briefly for the proof strategy of the global hypothesis. We still use the notation N tilde. So this is indeed a long time behavior for the equation in tau. We first study a simpler case when N tilde is always 0. That is the internal blow up case. And then the equation in tau will simplify to this equation. I will label it as equation L. I will first give a detailed study for this equation. And then we can, for the general case, we can rewrite the equation in tau as the equation L with some terms involving N tilde. And suppose T star is not infinity, and we will get a smoothness of N tilde in the long term. So this infinite interval is finite. So this term will goes to 0 as time evolves. And then the long time behavior of equation in tau will be dominated by the equation L. And then we can give a contradiction when the B is less than that crucial value. And to turn this intuition into rigorous proof, we adopt various estimates developed for the classical solution for the equation in T, like the entropy estimate and the super solution techniques. And to summarize, the blow up of the fan rate mathematically stops the classical solution and is related to the centralization. And in this work, we propose a generalized solution by considering this introducing a new time scale. And in our generalized solution, the blow up, the density function has a jump when the fan rate blow up, but this jump will dilate it to a continuous dynamic in an interval in the new time scale. And to prove the global hypothesis in the original time scale, this relates to the long time behavior in the new time scale. And it's worth mentioning that there are two very recent preprints also use this idea of introducing a new time scale. But we study essentially different generalized solutions, and one difference comes from that we rewrite this direct source term. So there can be various generalized solutions, and therefore an interesting question is to consider physical criteria which can identify a physical solution when they are in a certain context, and another interesting question is to consider the long-time behavior for the generalized solution. And welcome to read our paper on arXiv, and thanks for your attention.
Thank you so much, John, for your talk. I think we have time for one quick question, if anyone has a question. If you have, you can just unmute yourself.
Yeah, I have a question. I mean,
Yeah.
how you get the idea of this new time scale which you introduced here?
Actually, we see this from a simpler model, which is we consider just the advection equation like partial t p plus n of t plus 1. The velocity is just n of t plus 1, and there's only an advection term. And we encounter this model in a different problem, and in that problem in that case it's very natural to divide everything by n plus 1, because there's only the advection term is like n plus 1 partial v, and which is very natural to divide everything by n plus 1. And then we think maybe we can use this to on the NLF model. Let me find that paper. It's still during the we work on another problem, and there's a toy model which is nature to divide everything by n plus 1.
Okay. So you got idea from that model, and then you try to implement it in your model, and it works. Okay, thank you.
Thanks for the question.
Thank you. We have time for a super quick question.
I have another quick question.
Okay.
To have a fixed point for finding the n of t when you have a1 which is positive, can you have
Yes.
a case where you have multiple solutions, or can you avoid this? In principle, nothing prevents a case where you have multiple solutions for n of t when it's n equals something dependent on n. There you have this one, n of t equals minus a0 plus a1n. If a1 is positive, can you have a case where you have multiple solutions there, which will be another problem for existence?
No, we just interpret that if this constraint is satisfied, then n of t is given by this function, and if this constraint is valid, then n of t is infinity.
Okay. So it's, I wanted to be sure it's not an issue in the.
There is no multi-solution from this equation.
Okay, thank you.
Okay, so thank you again, John. I think we have to go on to the next speaker. And the next speaker is Pierre Roux.
Yeah.
So you can share your screen. He's in the University of Oxford, and he's going to talk about a project that we have together, I think.
Yeah.
Yes.
You can see your name is there.
Yes, go ahead, Pierre.
Plain screen. Is it okay?
Yes, good.
Okay.
So the floor is yours.
Thank you. So yeah, we talk about a recent work deposited in the archive about 2 months earlier, which is a joint work with José Antonio Carrillo, my postdoc supervisor in Oxford, and Susanne Solem, who is the chairman today. And it's about modeling grid cells. I don't know if you heard of grid cells, because they make some noise this time. To make a player for you, sorry. So grid cells are a specific type of neurons that you can find in the entorhinal cortex, which is a part of the temporal lobe, so in the bottom part of the brain. And they are believed to be pivotal in helping mammals orientate in physical space. So basically, they function as part of the positioning system in the brain of many mammals. They were found in rodents, bats, monkeys, and also humans. They were discovered in Norway around like beginning of the millennium. And the way they seem to perform is that the animal can integrate information from the firing of the grid cells, and the firing is dependent on the spatial position. So you can see, for example, on the left, the square is a physical space. The black path is the real-life trajectory of a real-life rat. And the red on the path, along the path, is one specific grid cells chosen at random, firing. So when it's red, the cell is intensely firing. And you can see that it fires at specific location in space. And if you draw it, and it's a right picture, the autocorrelogram of this cell, so which is when it's correlated to itself, you can see that the firing of one of these cells, of those cells, pave the space in the hexagonal way. So you have this very characteristic hexagonal pattern. So this is one cell, and the red parts are where it fires the most, and the blue parts where it's more quiet. And it's a very strange phenomenon, and a good way to try to understand that is to proceed via continuum dynamics. First with stochastic processes and then partial differential equations to try to have a global picture of how those cells could interact to produce those characteristic patterns. There are evidence, for example, this paper recently published in Nature, Gardner et al., that the connectivity of grid cells could be a torus, so a two-dimensional torus for rats, for example. And so it's not sure, like you have a lot of controversy, and so it's a very active field of research, but it's a nice hypothesis to test. Assume the grid cells are connected in a toroidal fashion, and let's see if we can reproduce this activity. So a PD system was derived through the mean field limit of a particle systems by José Antonio Carrillo, Andrea Clini, and Susana Solem. So it's a paper already on the archive, and Carrillo, Holden, and Solem published a second paper which studies this PD system. What this system describes is the probability density at each time, at each location of finding a neuron, which neuronal activity is S. The neuronal activity being a kind of firing rate, like if the number of spikes per second. So it's the active frequency of the firing for the cells. And this model reproduces very well this hexagonal firing pattern. So you can see the gray line in the middle of the picture. The gray line is the real life path of the real life rat, but this time the red along the path is not the real life firing of a neuron in the rat, but the prediction of the model of the firing of this green neuron. So it's tiny. I don't know if you see it well, but on the left, you have a square. So this is not physical space. On the left, it's the neurons arranged in a torus. So you have periodic boundary conditions. And you take one at random, for example, in the middle, and you see when it's firing. So when the rat moves, this pattern in the left moves, and the neuron, the green neuron, fires, like goes from the red to the blue part and fires differently. So I can try to share a GIF to show you how it can look like when the rat is firing. Where is the no? I want to. Sorry. I share. Yeah, this. Can you see the animation? Yeah. So you can see the rat moves. The firing pattern in space. So each point in space contains a lot of neurons. So you can see it either on a square or projected on a torus. And the point in the middle goes from firing very low firing when it's in a blue part, and when it moves, it goes into a red part and it fires more. And so you can see the animal can orientate itself by integrating how many like red dots it crosses. And so it means I have crossed that many like physical space distance. So you have, if you link it to other parts of the brains with integration processes, it makes sense that you can try to orientate yourself this way. So now let's see what this model looks like and how you can you can do some math on it. So plain screen, yeah. So the model contains four directions because you have different neurons with orientation preference, and to simplify, we consider only the cardinal points north, south, east, west. And you have a Fokker-Planck type equations akin to the one proposed by Delphine Salor and Xuan Du in the two previous talks. Just this type, we do not consider voltage, but activity of the neurons. And so we don't have exactly the same structure. You have derivative in time of the density, a shift, and the noise, which is with strength sigma. And this red strength of the noise sigma is will be very important in our analysis. So it's driven by a firing rate, which is space dependent and acts through a convolution. So you have these W beta, four of them, which are the connectivity kernel, and each of them is in the preferred difference, so north, south, east, west. So basically, you have integration of all the points through a convolution and all of the four directions through a sum, and then you input it into the drift for the activity. And the input of the rat is in this b beta of t. So basically, the movement of the head of the rat and its speed are contained into the external function b of t in this part. And then the red part here is the average of the activity, which means that the model, like the convolution is not for each S, it's you look at the average activity at other points, which makes sense, like where you have connections between locations in the grid set module, and you in each point see the averages of activity at each other point. And then you have a non-local boundary condition to ensure that the activity doesn't become negative, which wouldn't make any sense whatsoever. And the system is a little bit complicated. So what we will do to perform mathematical analysis is to simplify it to only one direction. And you can check on our paper on the archive that, in fact, you can generalize the mathematical analysis for one direction to four directions without a lot more computations. So the strategy to try to identify this specific hexagonal firing pattern is to vary the noise parameter. You can see here in the previous study by Carrillo, Holden, and Solem that when you change the noise parameter, you lose the hexagonal shape. Like when sigma reaches 0.02, you have almost lost the specific pattern that helps the animal orientate in space. But you can see that if you just change a little bit the noise, it's kind of robust. So what we expect is that there is a critical value of the noise parameter, which make the pattern disappear completely, and then the only stationary state of the equation becomes a flat state, like flat in space, all neurons do the same. And when the noise goes below some threshold, a bifurcation threshold, then you have a non-constant stationary state appearing. And so it's a strategy we will employ to prove the existence of a non-constant stationary state, so pattern activity, and then try to see if the method yields some information about what this pattern activity look like and how can we relate it to these hexagons. So as I told you, let's consider this simpler one component model. So we remove the four directions, just one, all the neurons are the same. They are connected still through the convolution and the average. So your firing rate in purple here is connected to all of our neurons, like is a sum of the activity of the whole network, but it's different at each point. And you have still the nonlinear boundary conditions. And if you solve the equation for stationary states, you can see that it simplifies to this thanks to the boundary condition. Then you can integrate this ODE because this phi doesn't depend on S thanks to the average. And so you see that stationary states satisfy this fixed point function, there are zeros of this fixed point functional, where this Z, thanks to mass conservation of the equation, must be this quantity. So then you have a functional and you are reduced to found the zeros of this functional. And the problem is that it's still a little bit difficult because you have two variables, S and X. So you can simplify it by averaging this functional, because you can see that this phi rho bar depends only on the average rho bar. So if you integrate, you multiply by S and integrate, you get a fixed point only in terms of one variable X. So let's introduce for convenience this k pi equals 1 over sigma. It's to avoid like nasty derivatives of the type 1 over sigma squared. And write this fixed point functional for the average of the stationary state. Okay. And so now we have this functional. We want some proper functional analysis framework to try to study it. So first, we consider average negative connectivity kernel. And for these kernels, you always have a unique stationary state, which is constant in space. So it will be our flat state, the standard space. It depends on the noise, on 1 over the noise. But you can build a lot of estimates with some effort about it. And we will try to prove that you have a bifurcating branch from this state. You can see that we have to define the firing rate associated to the stationary state and its derivatives. Then you specify the space in which you want to work. And why this subset of L2? Because you may guess that if you have a stationary state which is non-constant, each translation of it is still a stationary state because the equation is translation invariant. So you want to fix the center, basically. So you say, I want only component-wise symmetric functions. So instead of a continuum of stationary states, you have only two, one and the antipodal like transformation of it. And then we have this Hilbert basis of this L2S space of the torus, which contains only cosines because the sines are not present in this one. And now, and the Fourier coefficients, of course, which will play a major role in our analysis. And now we want to apply this ugly theorem. So don't dive into it too much, just you have two hypotheses, like the kernel of the Frechet derivative of the functional is one-dimensional, and the vector that supports it, if you apply the cross derivative, like in rho bar kappa, it doesn't belong to the image of the rho bar derivative. So you have two conditions, and if you satisfy them, you have the nice conclusion, which is from the trivial branch. So here in the theorem, we assume that the trivial branch is 0, so we will rescale to obtain that. The trivial branch bifurcates, and you have a non-constant branch of stationary states that are solutions to the functional equals 0. And in the neighborhood of the bifurcating point, it's the only possible solution. So of course, the only possible solution in the space L2S, which is why you can expect that then you have other solutions in L2, which are the translations of it and perhaps other things. So to apply this, we have to compute the rho bar derivative, so Frechet derivative of the functional, which describes the stationary states. And with quite a lot of work, so you can see the dog is crying because you have to go through a lot of pain to compute and simplify the terms. And this is a computation adverse dog like me. But you may end up with this naive formulation with here this phi prime 0, which is the modulation function phi applied to the constant stationary state. 1 minus something that depends only on the constant stationary state, the constant stationary state firing rate, and the noise parameter. And here you have this convolution of W with a test function, H1 in L2S. Then you define this functional to rescale in order to satisfy the hypothesis of the Crandall-Rabinowitz theorem to have a trivial stationary state at 0. So you can see that if rho bar equals 0, you are a 0 of H for each kappa. And then you have the cross derivative, which is a nightmare and which is most of the work, but it's not very interesting. Like it contains no like deep information. It's just you have to ensure that the condition, the second order condition holds to apply the theorem. But the most interesting part is a blue part. So all the information in this is in this blue part, because what you want is a one-dimensional kernel for the first order rho bar derivative. And to achieve that, you can notice that if you diagonalize this operator by taking H1, one of the elements of the Hilbert basis of the cosines, then you get a Fourier mode of W times this blue thing. So it gives you this, that if 1 over the blue part is equal to a Fourier mode, so a positive Fourier mode, because one of the parts can be proved to be positive, and the theta of k star is just a renormalization factor to ensure that like the cosine thing is in is of norm 1. Then you can prove that you have a bifurcation. So a non-trivial, a curve of non-trivial stationary states, curve depending on the noise. And you have additional information given by bifurcation theory that close to the bifurcation point, your non-constant stationary states, so your pattern activity, looks like the Fourier mode that supports the bifurcation. And you may want to know that this condition happens. So you can see that the blue curve is the blue part, and the horizontal lines are the Fourier modes, the renormalized, like Fourier modes divided by the renormalization factor. And you can see you have multiple crossing, each crossing yielding a bifurcation. If the kernel is of dimension 1, in some cases, through symmetry arguments, you can handle kernels of higher dimension by quotienting more the space. But basically, you can consider like some of the first Fourier modes. So in the top part, also this part is not interesting. This part is more interesting, that some of the first Fourier modes, so 4-1, 1-4, and 3-3, yield this nice figure. So, and it makes sense because it makes sense to sum them, because for other type of systems, it has been proved that you can have a resonance of the first bifurcations that combines into like new stationary states that contains information from all of them. And if you look at this time evolution of system from a constant state, which is unstable for small enough noise, you can see that the fourth panel in the bottom left part looks a lot like this. In fact, it's very close in spirit. And the dynamics spend some time here before going to the hexagonal pattern. And another nice thing is that if you take this cosine thing and you add the sines, which are not in L2S, so we cannot obtain something that contains them, then you have the hexagons. So it indicates, and it could be like further work, that you may be able to obtain the hexagons either by considering a larger space and performing a more complex bifurcation analysis, or by finding a symmetry breaking bifurcation that goes from there to the hexagonal pattern. And then we have yet to explain why this pattern is more stable, and how when you input the trajectory of the rats, you get it moves around without being destroyed. So some kind of stability with respect to a change in the external input. And I will finish with this more complex bifurcation numerical bifurcation analysis in the paper by Carrillo, Holden, and Solem, where you can see that probably the phase transition here, the first one, is discontinuous. The red dot on the horizontal line being the loss of linear stability, which coincides with the first bifurcation. And you can see that you have non-constant stationary states appearing for the nonlinear model way before the first bifurcation when the noise decreases. So probably you have some like subcritical bifurcation here, and then it connects here, and we don't see this. So we have to redo this kind of numerical simulations in a way more careful way to try to capture the unstable branches and to complete the picture, both numerically and analytically. So for the perspectives, we are working already on well-posedness and long time asymptotics for the time evolution problem. And we have to better understand the formation stability of the hexagons, have a better bifurcation diagram, study discontinuous fast transitions, which can be very hard when you don't have an energy structure like a gradient flow or something that helps you, and put back the time-dependent B of t or coupling with other type of neurons that are involved in this process. Thank you very much.
Thank you so much, Pierre. So we're slightly behind schedule, so I think we have to skip questions here too and go on to the last speaker. So then, Pierre, you have to stop sharing.
Yeah.
So that Alain can start sharing. So the last speaker of this session is Alain Blaustein from the University in Toulouse. And he will talk about concentration phenomena in the Fitzhugh-Nagumo network. In a Fitzhugh-Nagumo network. So go ahead, Alain. You have to unmute yourself.
Okay, yeah. Sorry, I was trying to find the button. So let me... Okay. So thank you. I would like to first I would like to thank the organizers for giving me the opportunity to present my talk, and especially you, Suzanne, who invited me to this very nice conference. And yeah, I will present you the works I've been doing on this these Fitzhugh-Nagumo neural networks. And first, let me give you a brief global introduction of the things we will be talking about. So our purpose here is to describe neural networks. And in order for this to be done, we consider, there are different scales at which we can describe those networks. So first, let me start with the microscopic scale, which focuses on the behavior of each individual neuron, and which can be very intricate to study when the number of neurons is large, since it contains a lot of information. Then on the left side of the picture, there is the macroscopic scale, which displays integrated quantities, so averaged, which are very interesting because they are supposed to be the ones that we can measure in experiments. So this is the scale we are interested in. And in the middle, there is the so-called mesoscopic scale, which is, so to say, artificial, since it is in some sense built in order to link the microscopic scale to the macroscopic scale. So it contains less information than the microscopic scale, but it's still quite complicated. And the purpose of the presentation is to explain the links between in our setting, of course, between the mesoscopic scale and the macroscopic scale. So more precisely, I will study a precise regime. And we will see that in this regime, the mesoscopic scale can be approximated by an asymptotic model, which is the macroscopic one. All right, so as I told you, there are those 3 different scales, and let me start by introducing you to the microscopic scale. And in order to do this, I need to tell you how to model how one neuron behaves. So now I will present you how a single neuron behaves. And what we're interested in this talk, the quantity we want to study is the voltage through the membrane of a neuron, because information in brain is propagated through voltage and variations of voltage. And so the models that we're using come back from the 50s and from the pioneer work of Hodgkin and Huxley, who built a very precise model which describes the dynamics of the voltage through the membrane of a neuron. And let me start by showing you some an illustration of this these dynamics. So here, I hope you see. You can see that on the x-axis you have the time, and on the y-axis you have the voltage. So this graph represents the evolution of the voltage through time. And here on the top of the picture, you can see that there is a constant current, which is the current that is applied to the neuron, and which is constant through time. So basically what this simulation shows is the evolution, the reaction of the neuron towards a constant current. So basically they plug, you can think that they plug the neuron to an input current and see what happens. So when the current, the input is low, the neuron just relaxes to equilibrium, as you can see. But when you increase the current, you can see that there are some spikes that appear. And so the neuron spikes and then comes back to equilibrium. So this looks like what Delphine showed at the beginning. And this kind of behavior, this is the kind of behavior we will be interested in. And if you keep increasing the current, the input current, then after a certain threshold, you can see that there are some periodic behaviors that appear. So the neuron basically keeps spiking, and you have those patterns that appears. So here are the main characteristics of the model that Hodgkin and Huxley built. And now I come back to my presentation. Yeah. Okay. So the problem, so this model, the Hodgkin and Huxley model, is very precise, but the problem with this model is that it's complicated, mathematically speaking. So Fitzhugh and Nagumo built a simplified version, which is supposed to keep the main features that we talked about, so the spiking and the periodic behavior. And here I wrote the Fitzhugh-Nagumo model. So it's a couple of, it's a differential equation with 2 components. So the first one is VT, which stands for voltage. So it's the quantity we're interested in. And the second one is WT, which I will call the adaptation variable, and which is here to capture those periodic behavior. Indeed, if you only have one component, a first order ODE, you cannot get those periodic behavior. So the simplest way to get those periodic behavior is to add a component, and you get a second order ODE, and hence you get those periodic behavior. So this is the role of this WT, and it is supposed to mimicate the gating variables in the Hodgkin and Huxley model. All right, then I need to explain you what are the coefficient of the equation. So you have these n and a is a linear map, whereas n is nonlinear. So it's typically v minus v cubed. And they have in common that they are both, they have confining properties. So they bring you back to equilibrium in order to get that relaxation to equilibrium after spiking. And so here on A, the confining property comes from the fact that you have minus B with B positive. And on N, you have a nonlinear confining property coming from the minus V cube, which brings you back very quickly to equilibrium, as we've seen in the simulations. And lastly, I want to point out that we added some noise on the voltage variable in order to take into account the random fluctuations of the potential, which our model doesn't take into account. So there are a lot of discussions about whether this noise is relevant and where to put it. Some people put it on the W variable, but in this talk, it's very important to have it on the V variable. Our analysis relies on this. And the external inputs, Ix, represent this constant current which we plugged the neuron to. All right, so now you have the behavior of a single neuron, but we're interested in a network of neurons. So we consider now a network composed of n neurons, and we say that they interact with each other, and their interaction is governed by Ohm's law. So now the external input that receives neuron I is given by an average of all the interaction with between neuron I and its neighbors, neuron J's. And I said that the interactions are governed by Ohm's law because you can see that you have a difference of potential here. And the coefficient that multiplies this difference of potential, which tells you how strong is the connection between neuron I and neuron J, is given by an interaction kernel, phi. And so this represents the conductance, and it depends on the spatial location of neuron. So you have, in fact, a spatially extended neural network, and the interaction between neurons depend on their spatial location. All right, so this is the full microscopic model. And now let me present you the mesoscopic scale, so the intermediate scale that I've talked to you about. And it is obtained as the number of neurons composing the network grows to infinity. So on the latter model, if you say that the numbers of neurons which compose the network goes to infinity, then you can see that the dynamics of the network are well described by a distribution F. So it's F of TXVW, and it represents the probability of finding a neuron at time t and position x with a potential variable V and an adaptation variable W. And the dynamics of F are driven by this mean field equation, I call it. And so it's basically the same equation as before, but you replace the interaction term, which was a sum, by an integral, since you went from a discrete setting to a continuous one. So now, instead of summing, you integrate the interactions over all positions and all voltage and adaptation variable. And also you replace the noise by a diffusion term with respect to V. So you get a diffusion term only with respect to V because there is only a Brownian motion with respect to the V variable. So this derivation has been made rigorously in several works. and in different settings. But I won't be focusing on this part of the job right now. I want to explain you the links between the mesoscopic scale and the macroscopic scale. So I told you that the macroscopic scale is obtained in a particular regime, and let me introduce you to the regime I'll be talking about. So what we say is that the interactions between neurons are divided in two categories. So the first category is are weak long-range interactions. So we say that they have long range, but they are weak in the sense that this interaction kernel psi is more regular or smooth in a sense that needs to be precise. And the other type of interaction are the strong short-range interactions. So I say that they are short because the delta zero stands for direct mass. So here, only neuron at the same spatial location interacts with each others. And they are strong because there is this multiplier 1 over epsilon, and epsilon is meant to go to 0. So if we rewrite the equation with this nzets on the interaction kernel, we get the same equation on the left-hand side and an additional term, which I put on the right-hand side, and which is the leading order of the equation with respect to epsilon, because you have a 1 over epsilon. And it displays, so this term is due to, of course, it is due to strong short-range interactions, and it displays the macroscopic density associated to the network. So there is this rho 0, which is the spatial distribution of neurons, and this capital V epsilon, which is the mean voltage at spatial location X in time t. So this is exactly what you get, and our goal here is to describe the dynamics of the network in the regime where strong short-range interactions dominate. That is when epsilon goes to 0. So let me explain you formally what happens. So in the limit epsilon goes to 0, we expect f epsilon, that f epsilon should converge to something that cancels the leading order in epsilon, so the right-hand side of the equation. So that means that as epsilon goes to 0, phi minus capital V epsilon times f epsilon should be very small. And this, since f epsilon is a probability distribution, this exactly means that f epsilon looks like a direct mass centered at capital V epsilon times its marginal with respect to the adaptation variable. So capital F epsilon is just F epsilon integrated with respect to V. So this, if you carry this analysis until the end, you get that F epsilon converges indeed to a direct mass centered at limiting capital V times a limiting distribution capital F with respect to the adaptation variable. And this couple capital V capital F solves a system which is a nonlinear coupled nonlinear system. So V solves the reaction diffusion equation because you have this interaction, this term here, which is an integral term with respect to the spatial variable, and it is coupled with a transport equation which is solved by capital F. And I should mention that if you take the average, so capital W of capital F, then the system capital V capital W solves the classical, what I call classical Fitzsigs-Nagumo system. Okay, so this is where I started. So this is where I started. It was already, this work had already been done by Creva, Fay, and Filbé in a setting without the diffusion term. So here for this analysis, the diffusion term doesn't matter. And they proved rigorously this convergence. And so they prove basically that F epsilon concentrates with respect to the potential variable V. This is why we say that we study concentration phenomena. And now the question I tackled on that subject was to study the profile of concentration. So once you know that the voltage distribution concentrates into a direct mass, you can wonder what's the profile of this concentration. So this is basically the limiting, the direct mass is the first order in the limit of F epsilon, and the profile should be the second order. And here I just gave you two pictures. On the left side, concentration occurring with the Gaussian profile, and on the right side with the triangular profile. Yeah, so let me again formally explain you what happens. And this is where the diffusion term gets important, because this is the diffusion with respect to V is the term that drives the profile. So indeed, if this is just formal, but if we gather the leading order with respect to epsilon with the diffusion term, and we put them together, you can see that the right-hand side is cancelled by Maxwellian. So the functions that cancel the right-hand side are of the following form: exponential minus V squared, basically. So what you expect is that F epsilon will look like a Maxwellian centered at capital V epsilon, with a Maxwellian with the vanishing variance, to say that it concentrates, times its marginal with respect to W. Okay, so my goal here is to rigorously justify this convergence, and I see I'm running out of time, so I will quickly present you the results. So we had several approaches to justify this limit. And the first one was what I called Hamilton-Jacobi approach. So the idea is to study what we call a Hopf transform phi epsilon of F epsilon. So you say that F epsilon is an exponential of 1 over epsilon times phi epsilon, and you want to go through the convergence analysis of phi epsilon. And basically, if you manage to prove that phi epsilon looks like a quadratic function of this type, then you're done, because if I go back here, you get exactly what was on the formal the computations. And this is what we are doing. So this is a work in preparation that I did with Émeric Bouin. So we proved that if you take the Hopf transform close enough, very close to the limits, then this propagates with respect to time, meaning that for all time t, the Hopf transform will converge to the limit you expected, and you get the convergence with the rate. So you get a rate of convergence, which is not usual when you follow those type of approaches. But there are some disadvantages to this approach, which are that it holds in a perturbative setting. So the constraint is quite you cannot consider general initial data, and you don't see what happens with respect to the adaptation variable W, because the limit doesn't depend on W anymore. So I see. So I will now conclude, because I don't have much time left. So I wanted to explain the proof, but just to tell you that we did another approach. and this other approach, so the weak convergence, we derived. So I said that there were some disadvantages on the Hamilton-Jacobi approach. First, that it holds in a perturbative setting, and then that we don't describe the dynamics with respect to the adaptation variable. And we filled these gaps in a second result following what I called the kinetic approach, in which we proved the full convergence of F epsilon and completed the first result that I presented you. And I will stop here. Thank you very much for your attention.
Thank you so much, Alain. Any questions?
Tell us a bit more about the proof that you wanted to talk about.
Oh.
Yeah, you can do that. We have a few minutes.
Okay, thank you. Okay, so so we want to prove that phi epsilon converges to this limit. So basically, what we did, and to obtain explicit convergence rates. So basically, what we did is that we performed the Hilbert expansion of phi epsilon. So we said that it looks like the limit plus a perturbation of order epsilon. And now the proof comes down to show that this perturbation phi epsilon 1 is uniformly bounded with respect to epsilon. If you do this, then you're done and you prove the theorem. So you write the equation on phi epsilon 1, and you see that it writes like some terms that are not stiff, that are of order 0 with respect to epsilon, and some other terms that are of order 1 over epsilon. And so you guess that this operator J epsilon 1 will tell you how behaves the perturbation. And the idea was to look for the function that cancel this operator, and then you prove that the phi epsilon 1 is bounded by building some sub and super solution to the full equation of the form phi 1, which is the function that canceled the J epsilon 1, plus or minus, depending on sub or super solution, some function that needs to be determined. So this, and then you look for the right phi, and you try to close the estimate. And once you have those sub and super solution, then you apply a comparison principle that ensures that the real solution phi epsilon 1 is in between those sub and super solution. So yeah, this is the global idea.
Oh, thank you.
If I may ask a question. So you talked about different metrics, right? So weak convergence, strong convergence.
Yeah.
Wasserstein metric, I guess, and L1 or L infinity.
Yeah.
So where you lose the order, it is let's say if you dominate the weak convergence by some or the relative entropy or something like this by the strong metric, or is it somewhere coming from somewhere else?
So maybe I went, I'm sorry, I went really quickly on this part. So the L infinity convergence, I meant the convergence of phi epsilon. So
yes.
the first result that I showed.
Yeah.
And so there are those disadvantages I talked about,
yes.
And we tried to build another method where the first thing we did is to provide a weak convergence result for F epsilon. So this is in Wasserstein metric, and you don't have those the disadvantages anymore. You don't the results hold true in for general initial conditions, not in a perturbative setting. And you say what happens with respect to the adaptation variable W. And then
and you have a better rate, right? Don't you?
I mean, no, you still have epsilon.
Ah, then I didn't get it. Okay. So
But,
that's the same rate with respect to epsilon, the convergence.
Yeah.
Oh, okay.
But indeed, then it was only weak convergence. So we strengthen this result into a strong convergence, L1 convergence, which I didn't present here because we didn't have time. But with a deteriorated convergence rate. So if you try to get strong convergence, you lose on the rate of convergence.
Yeah. Okay, thank you. So sorry, just a follow-up question. So could you cook up an example where you could come up with, I mean, working on psi a little bit on the interaction kernel, where you probably ultimately would end up with a weak convergence but not strong convergence?
So in what I presented you, the assumptions on the kernel are quite general already. So let me come back. And this is what we wanted to keep it general. Sure. In order to cover a wide range of interactions. So this interaction kernel is not supposed to be symmetric. So it's not symmetric with respect to x and x prime. And we only assume some integrability conditions on psi. So I would guess, which are no continuous, there is no continuity required. And so I would say that it would need to be very at least very rough to not have the strong convergence because we proved it with our hypothesis. But I don't know, I'm not sure, so I can't answer very precisely.
Thank you.
Thank you.
Okay, so I think we'll stop the session there and give ourselves a short break until the other group is ready. Maybe you want to take over, Daniel?
Yes, thank you, Suzanne, and thank you all the speakers of this very interesting session. So the other channel are telling me that they're running slightly late. So the idea is I'll ask Thomas, sir, our next speaker, to unmute himself and switch on their camera, and then we will set up everything and perhaps wait a few minutes.
I'm here. Can you hear me?
Hi.
Hi.
There you are.
Can you hear me?
Yes, very well.
Perfect. Excellent. And then let me try to share my screen. Sorry. All right. Can you see my screen?
We see it in full screen at the moment. Yes.
Okay.
So we can see your pointer and your videos.
Video is playing. Okay, perfect. All right.
1 second. The video seems to be a bit. Can you try that? Is it meant to be flashing?
Yes.
If so, yes. Yes.
Okay.
Then that's correct. Yes.
All right. So I'm here. I'll just.
So I think I think there will be a few moments of embarrassing silence, and we wait that the others join us from the other channel.
All right.
And while we are at it, so we give flexibility to our speakers as to whether they want to collect questions at the end, or if some people prefer having them as they come, perhaps filtered through us. So can you tell me what's your take on it?
Absolutely. I'm all for, I'm all for interruption and questions. Yeah.
Okay. So I'll basically state that people.
Yeah. I mean, they should feel free to interrupt.
So I will basically tell people at the beginning that they're welcome to put questions in the chat at any time, and then I eventually will relay them to you.
Perfect.
Yeah, is that right?
Yes,
yeah?
That sounds perfect.
Okay, so I'm receiving the news that the other group is shutting down the channel and they're about to come here.
All right.
And just for the sake of it, you could probably, I think you should consider to still have a full hour from when we start, Thomas. I think we are.
Okay.
Yeah. I think we can start. So it is my pleasure to introduce today's plenary speaker, Thomas Serre. Thomas is a professor of cognitive linguistic and psychological sciences and a professor of computer science. And he's also an AI chair within the Artificial and Natural Intelligence Toulouse Institute in France. He received a PhD in neuroscience from MIT in 2006, and his research seeks to understand the neural computation supporting visual perception. His work on visual perception has been featured in the BBC series Visions for the Future, in The Economist, The New Science, The Scientific American, and many others. Today, Thomas is going to talk about beyond feed-forward processing on the role of feedback mechanisms in visual recognition. Thomas, we are thrilled to have you with us, and the floor is yours.
Well, thank you so
One
much.
thing I should say, actually, before letting you speak, for those who have arrived late, is that we are welcoming questions at any time. So if you put them in the chat, I will collect them and relay them to this, to Thomas at any time. And now, really, the floor is yours.
Thank you so much. Thank you so much to the organizers for their kind invitation, and thank you, Daniele, for hosting this session. So I'm going to tell you about vision, and one of my favorite experimental paradigm to study vision is this one, and I hope you can all see the videos here. So just to give you a preview or some sense of what to expect, you're going to see images here on the left flash very briefly, and so the rule of the game is essentially for visual observer, visual participants to report the presence or absence of a particular category of objects. In this case, for instance, reporting whether they saw an animal or not. And so here images are flashed, somewhere around 100 milliseconds or so. In the lab, we could make this task, way faster. We could flash images for, a dozen or so milliseconds. And probably, given the latency, the bandwidth, I don't know what the quality of those images are for you, but again, in a lab setting, actually, interestingly, participants report typically not to see anything at all because it goes so fast. But we ask them to, and we force a response from them, and sure enough, they respond much more accurately than chance, probably around 80–90%, as to whether they saw an animal or not in those images. And so what is revealing about this particular experimental paradigm is that, as we all know, vision is a very complex function. The underlying visual dynamics is quite complex, yet we can push the visual system to its temporal limit with this kind of rapid categorization paradigm. And when we do so, obviously people start making mistakes. The visual system is operating in a very kind of impoverished context and environment, but we can study vision at its core. We can study the base representation that are being built by our visual system before more complex visual routines takes place, before we can move our eyes, shift of attention, etc., etc. Obviously, not only are human observers able to solve this complex rapid visual categorization task, but it's also quite possible to train primates, and monkeys in particular, to solve this task. I'll just show you here a quick demo where you see a monkey here. This is work done in the lab of Denis Fize in Toulouse. but they were able to train monkeys to solve these kinds of tasks. Here it goes so fast that probably, at the frame rate that we're getting through Zoom, you're probably not even able to see the image, but the monkeys have no problem solving this task. And in fact, potentially because their brain are about 50% smaller than our own brains, they tend to be about 50% faster than humans on this task. So what are the computational mechanisms underlying our ability to solve this rapid visual categorization task? The past several decades of work in visual neuroscience have pointed to a set of visual areas that fall along a particular anatomical section of our visual system known as the ventral stream of the visual cortex, which starts from the back of your head and runs laterally towards the side of your head. Starts at the level in the cortex, at the level of the primary visual cortex, run through secondary visual area V4, and then culminate at the level of the inferior temporal cortex or IT cortex. Again, I don't know how many of the people here in the audience know about vision, but I think most people are familiar with the underlying kind of ideas behind the set of neuroscience facts that the past several decades of neuroscience work have revealed. We know that throughout this ventral stream, the visual signal undergo a series of transformations whereby the visual representations get more and more complex. The preferred stimulus or the preferred selectivity of neurons get more and more complex, starting with something like flash of spots of lights in very early visual areas like the lateral geniculate nucleus and the output of the retina. We find like orientation selectivity for bars and gradings in the primary visual cortex. And then as we get into higher and higher areas of the ventral stream, one can start finding neurons selective for more and more complex stuff, like parts of objects, textures, and maybe for those objects that are ecologically important, entire objects like faces, body parts, and things of that sort. And then in parallel to this gradual increase in the complexity of the preferred representation comes a gradual increase in the invariance properties of the representation. So neurons not only are becoming selective for more and more complex stuff, but they do so in a way that is increasingly more invariant to 2D transformations. So why do we care about those ultra-rapid or rapid visual categorization tasks? Our visual system contains both feed-forward and feedback connections. So feed-forward connections run from lower visual areas onto higher visual areas. I'll tell you a little bit more in just a second about feedback connections, but feedback connections will run recurrently within local visual areas, as well as top-down from higher onto lower visual areas. And so while certainly we know that feedback connections play a critical role in visual processing, we know that given the speed and the latency and the onset of category information that can be decoded from visual areas, we know that at least to account for this rapid visual categorization task, potentially feedback mechanisms play a very minimal role, that potentially these core visual representations, this core ability to solve a rapid visual categorization would rely primarily on a single feed-forward sweep of activity from the retina through this ventral stream all the way to your hand pressing a button. Then just something to keep in mind when we look at the anatomy and physiology of the visual system, it's not easy to come up with an approximation of the number of processing stages, but I think most people, most visual neuroscientists would agree that somewhere around 5 to 8 processing stages is what is needed for the visual system to solve this rapid categorization type of problems. Again, throughout the years, we've had a zoo of computational models. I'm sure you've heard about Neocognitron, things like VisNet, SpikeNet. I did my PhD at MIT where I contributed to the development of a particular class of computational model known as HMax. The details don't really matter. What I think is an interesting kind of success story for computational neuroscience is that globally, this class of model has been able to account for a host of experimental data. And those models are feed-forward hierarchical models, and interestingly, they rely on, or they use only 4 operations in order to account for experimental data: linear filtering, followed by a nonlinear rectification, some form of divisive normalization, and some form of pooling. And just stacking these 4 operations, in a feed-forward manner through a cascade of those processing stages has been sufficient to account for a host of anatomical, physiological data. And then ultimately, and this was part of the focus of my PhD thesis, we've been able to show that when we train those models to solve this rapid animal and animal categorization task, we could account well for experimental data, human psychophysics data of the kind that I alluded to earlier. So in a sense, it seemed that we had kind of a nice story from a computational neuroscience. We understand fairly well the anatomy, physiology of our visual system. We can replicate this knowledge or summarize this knowledge into computational models that we can then simulate. And when we simulate them, we can then not only be consistent with the actual physiology, but also account for this high level kind of behavior such as visual image categorization. Now, most of the models that I mentioned were models developed, throughout the 90s and maybe, years 2000. We are in the era of deep learning. So fast forward, 10 years later, we're in the midst of this deep learning revolution. The ability of computer vision systems and in particular this deep neural network, as we know, increased dramatically. Obviously, one thing that has been powering this progress has been the rapid gains we have made in computing power. So what I'm showing here on the left is an example of a TPU, I believe, from Google, which is this kind of AI accelerator developed by Google. And of course, there are many others, including GPUs. And so this increase in computational power combined with very large data sets has really allowed computer vision scientists to develop systems that perform orders of magnitude better than this early kind of models of the visual system from 10, 15, 20 years ago. Now, if we look at one of the main ingredients that has accounted for this progress in the field, what I'm showing here is a plot corresponding to so the height of the bars correspond to error rates. So this is for a kind of a main computer vision challenge, which involved a data set called ImageNet. I'm sure most of the people here have heard about it. Every year people submit, their or run their system, and then, there is a winner. And so what you see here, the height of the bars correspond to the error rate of the winning architecture for that year. The x-axis correspond to the year of the competition, and then the name of the winner. So what's pretty clear is that over the past, since 2010, and especially since 2012, when the first, since the introduction of the first kind of deep neural network, which was AlexNet with 8 layers of processing, the accuracy or the error rate, I should say, has been going down steadily. I should point out that the 2016 was the last year that the competition was held. The data set is still being used in computer vision research, but 2016 is considered a landmark year because that's the first year that the systems achieved human level accuracy. And I'm not talking about human level accuracy on speeded visual presentation, as I showed you in my introduction, but I'm really talking about, allowing humans and giving humans all the time in the world to categorize images. And, we're at the level where the systems really match the level of accuracy of human observers. Perhaps more interestingly is to look at what's happening with this red plot here, red lines, which indicates the number of layers of the winning architecture that year. And so you see that we start with about 8 layers of processing with the AlexNet, and then years after years, there's a very clear trend whereby the best neural architectures end up getting deeper and deeper to the point where, modern days, I would say, deep convolutional neural networks are typically ensembles of networks that are themselves hundreds of layers deep. So this is equivalent to if not hundreds, maybe even thousands layers of processing. And if you do this, really impressive things happen. I think, none of the people that I know, and certainly not myself, but people who have been doing computer vision for the past 20 years or so, I don't think would have seen this coming. The progress has been staggering. I just mentioned that, modern computer vision systems are probably already outperforming humans on this ImageNet 1,000-way image classification. Facial recognition has followed a very similar trend. We have bigger and bigger data sets. Today, these data sets contain millions of individuals. Those neural networks can discriminate between millions of people at accuracies that are in the 90% or so of accuracy. And in fact, a study from a few years ago led by Jonathan Phillips, who is the person who has been working for the American government, who has been keeping track of the accuracy of leading facial recognition system for the past probably 20 or 30 years. And for the first time, the study has shown that the state of the art in facial recognition, the systems not only outperform you and I, kind of naive facial recognizers, but they can even compete with the best human facial recognizers we have, who are facial forensic experts. So people who recognize faces on a daily basis. So I think this is really, really impressive progress we've seen in the field. And yet, I think with all the excitement surrounding deep learning, the limitations of the systems is becoming increasingly more obvious. And so one of the key limitations, in my opinion, is the ability or the lack of ability of these systems to deal with novel, unknown degradations. And so I showed an example here on the right. This is a figure that I took from an old paper by Pavan Sinha, published in Nature Neuroscience many years ago. But I think it illustrates the robustness of our own visual system very well. So if you're old enough to know the people that are shown on these images, and when I show that to my undergrads, the most of them miss the point that I'm trying to make because they don't know the people. But hopefully, most of us here know these people. And so what is fascinating here is that you've potentially never seen those faces at such a low resolution. I think this is a 10 by 10 or 8 by 8 pixel here, and yet you can still recognize those faces. I'm quite sure that you've never seen faces at such a low level of such a high level, such a low frequency. And maybe even more impressive are those faces that have been stretched vertically. I'm quite sure that there is no way for you to have been exposed to those transformations naturally, and yet your visual system has this ability to somewhat undo the transformation and still recognize the faces. And I can guarantee you, we've done that kind of casually. We don't have anything published, but if you take any of these leading facial recognition systems that are outperforming human observers on those facial recognition tasks, they would fail miserably on any one of those transformations. This is also true in the case of object recognition. There's a more systematic study published a few years ago at NeurIPS by Garros and colleagues. And so they showed that, again, if you establish a baseline from human observers during this rapid categorization task, like your favorite deep neural network, they will outperform, so they human observers, so they call that superhuman performance. You can even degrade those images. You can apply very severe amount of Gaussian noise. And again, if you train the systems on those degradations, they will outperform human observers. But here's the catch here. If now you make a tiny little change between the kind of noise applied between training and test, and so here, I don't know what your screen resolution will be, but this is a salt and pepper noise here used for training on the left. This is Gaussian noise used for test. Even at a high resolution, those two types of noise are almost identical to a naked human eye, and yet that's enough to put this deep neural network at chance level, from superhuman level when trained on those degradations to chance level when they are not trained on. Okay, so neural networks, modern day deep neural networks, have this uncanny ability to really almost kind of rote memorize the source of noise or learn to deal with the source of noise that is present in their training data. But I think it's fair to say that they exhibit very limited ability to generalize beyond the training data, and certainly to generalize to the kinds of image degradations that they haven't seen during training. And just to open a parenthesis, I think this is one of the main reasons that we don't have self-driving cars at the moment. We have companies driving, around the world, collecting, humongous data sets, potentially, billions of labeled data, including all kinds of bootstrapping methods to really incorporate errors produced by those systems. But the visual world is just too large. There is never a training data set that is large enough to encompass all possible combinations of, objects and their degradations, all the possible visual illusions, etc., etc. Here's an example, perhaps a little bit more personal, and something that I'm very interested in is the so-called area of visual reasoning. So a very simple example of a visual reasoning ability would be the ability to learn to judge whether two or more shapes presented on the screen are same or different. There's a whole cognitive science literature. This is something that animals, even bees, newborn ducklings can do from birth. And so we wanted to ask whether, modern day visual deep neural networks can learn, visual reasoning, such a visual reasoning task. So the same different judgment. So there's a whole lot of systems that have been developed for visual question answering, which is closely related. So the idea is that those are systems that are trained to answer questions based on images that are given to them. So you can ask them, how many pizzas are in the image, or what's on the right of the dog, what is the dog sitting on, and so on and so forth. But the kind of dirty little secret is those computer vision systems, those deep neural networks, are always trained and tested on the same finite set, same vocabulary of shapes. So here's an example of a popular data set used in visual question answering known as Sort of Clever. So it's a data set made of simple geometric shapes, circles, square, different colors. And so you can really evaluate the systems to answer all kinds of questions based on, kind of toy world made of those shapes. But even though the systems are trained and tested on different samples, we realize that they're always trained and tested on samples derived from the same basic dictionary of shapes. And so my students ran a very simple experiment. They took what was at the time a state-of-the-art system for visual question answering. And so they train it to solve a same different task. So of course, the systems are never given the rule. They have to discover the rule from training data. And so if you train and test the system on the same set of shapes, you find that, if you wait long enough, they can certainly learn that. And by long enough, I mean, several hundreds of thousands of presentations. However, if we keep one single combination of shape and color out of the training data set, for instance, we train them on science and we train them on circles, maybe no science circle, we keep that combination out for tests, then we find that this system never generalizes to this left out condition. In other words, they can literally learn, or I like to say, rote memorize statistical associations between visual features and abstract rules, but they never really generalize beyond the visual appearance of those objects. Okay. And of course, this is in sharp contrast with the way animals learn to solve this task. What I showed here as an illustration is a study published in Science a few years ago, where they showed that they could take completely newborn ducklings and use what is called the imprinting, which is a natural response of the animal. When the duckling is born, the duckling will imprint on the first thing more or less that it sees, which is normally the mother, but you can shortcut that function and then imprint or allow the animal to imprint on objects, or in this case pairs of shapes, either being pairs of same shapes or pairs of different shapes. And then later on, you can evaluate you can give two choices, two sets of shapes to the animal, and then evaluate their ability to exhibit or have learned the same different task. And what they showed is that the duckling could, from a single training example, right? We're not talking about the hundreds of thousands of training examples here, but from a single training examples, the duckling was able to generalize beyond color or shape. So that's, orders and orders of magnitude better than almost anything you could get from modern day deep neural networks. I'll skip the details. We've done a lot of work on this. I'll just give you like the high level summary. We have shown computationally that in order for deep neural networks to learn to solve this task, there is a very simple mechanisms that can allow them to do this. And it's just allowing them to, or spoon feed them with a visual scene that has been perceptually organized for them. In other words, they would need an ability to attend to individual objects and solve the so-called binding problems. So learn to associate features to objects held into memory, and not simply, processing those images as one single kind of bag of visual features. Obviously, those functions, whether it's working memory or attention, relies on the cortical feedback that we know is present in our visual system. So just to give you a kind of a brief summary of what I've tried to tell you so far, we know that we have very successful deep feed-forward neural networks, CNNs, that are solving tasks that we thought would be very hard for any kind of engineered system to solve, visual tasks, that is, but they have become orders of magnitude deeper than our own visual system. As I mentioned earlier, when we look at the number of processing stages of in our visual system, we're probably close to half a dozen, maybe up to a dozen processing stages. And so the way our visual system is able to build some sort of a processing depth beyond this, initial feed-forward sweep is through reentrant signal, through feedback connections, right? So it's not just by, processing statically through layers, but really allowing signals to reentrant, which provides an ability to compute or obtain depth through time, through feedback connections. And so just maybe to give you a bit of terminology, I've been talking about feed-forward connections, so running from lower onto higher visual areas. We also consider, two kinds of feedback connections, what I'll refer to as top-down connections that run from higher level visual areas onto lower visual areas, as well as so-called horizontal, lateral, local recurrent connections, which runs within a processing stage. I'll tell you much more today about the role of horizontal connections, but hopefully if I have time, I'll tell you a little bit about top-down as we've done work involving both. So our starting point to try to extend this class of feed-forward hierarchical models to incorporate recurrent connections or feedback connections was really going back to square one and trying to really characterize low-level electrophysiology phenomena. And there's a whole list of phenomena that have been discovered and studied for the past several decades, which have to do with the so-called classical and extra-classical receptive fields phenomena. And I don't know how many of you have heard the term extra-classical receptive fields, but I'm assuming that most of you are familiar with the notion of the classical receptive field, which is the part of the visual field that needs to be stimulated for a particular neuron to respond. What people refer to as the extra-classical receptive field is an area of the visual space that typically sits outside of right around the classical receptive field. If you just stimulate the classical receptive field by itself, by definition, it will not elicit any response from the neuron. Otherwise, it would be part of the classical receptive field. However, if the classical receptive field is already stimulated, if there's something presented to the classical receptive field, then we know that what is also presented in the extra-classical receptive field just outside will have a very strong modulatory effect on the neuronal response. So and that's perhaps the only math, sadly, that I'm going to be showing you here, and without getting into much detail. But there is body of work that has suggested that this type of classical, extra-classical receptor field interactions rely on feedback connections, and in particular horizontal connections within neighboring neurons. And maybe something that I need to tell you, for those who are not familiar with the anatomy and physiology of the visual system, your visual system, and especially earlier areas of the visual system, are organized retinotopically and according to cortical columns. So you should think of those columns as each containing potentially hundreds, thousands of neurons with different selectivity. For instance, a range of neurons spanning all possible orientation tuning, or maybe all possible spatial frequency tuning, all possible color opponency tuning, so on and so forth. But typically they will include an entire battery of feature selectivity for that particular visual area. And then a particularity of neurons within cortical columns is that they all share the same receptor field. So the receptor fields are all centered at the same position in your visual field. And then those columns get replicated, right? Essentially they're going to tile your entire visual field. And so it is assumed that the pattern of connectivity between neurons, between nearby columns, are the main drivers behind this kind of classical, extra-classical receptor field phenomena. So a few years ago, we developed I would say dynamical system type of model to try to characterize the interactions between neurons within cortical columns and across cortical columns. So these are the equations describing the system. I just put them there because, you know, I know that there are mathematicians in the audience. I'm not going to tell you very much except to say that, you know, this is building on a long history of work. You know, people like Steve Grossberg, Sebastian Song, and many others. So these are systems of differential equations. You typically have, for every neuron, you're going to have one set of differential equations for governing the excitation to that neuron from horizontal connections, separate differential equation for the inhibition. And then the important thing here is maybe that, you know, those stars correspond to convolutions. So we are modeling horizontal interactions as a 3D tensor. And so the assumption is that the same kind of kernel or tensor applies at every location and governs the interactions between neighbors. And so now, you know, because of a large number of cortical columns spanning your visual field, we end up with, you know, a very large number of differential equations to solve. Historically, we used to use, you know, very simple method like Euler integration. But 2 points. One is that it ends up being fairly computationally intensive to simulate these kinds of models, and they are not very prone to learning and to optimizing the synaptic weights. And I'll get back to that in a second. Second of all, though, is that, you know, once you have populations of neurons or entire, you know, layers of processing endowed with this kind of dynamics, you can have very interesting, you know, phenomena that arise. You know, in particular, neurons can now communicate from one end of an image all the way to the other end of an image, right? As opposed to in a purely feed-forward model where the only way for neurons to incorporate increasingly large amount of context would be through feed-forward processes. Okay, so I'm not going to tell you anything else about the model. This is all published. All I'll say is that the particular pattern of connectivity, which is, you know, this tensor here, is an interesting piece. Everything was done by, you know, what we call graduate student descent. So I had a graduate student spending several months of his life looking for electrophysiology studies, trying to find constraint on the pattern of synaptic weights and the kinds of operations we should bake into the model. We ended up with 3 key mechanisms to account for this set of phenomena. We had to assume that the interactions between nearby columns is excitatory, where those columns are nearby. Past a critical distance, the interaction switches from excitatory to inhibitory. So neurons that are near excite each other, neurons that are far inhibit each other. Across cortical columns, the connections have to be tuned. So only units with the same selectivity are connected. So if you're a neuron here tuned to vertical orientation, then you're going to be connected to your neighbors, if and only if they are also tuned to a vertical orientation. And then the third key mechanism required in this model was the requirement that, unlike excitation that could be linear, inhibition had to be nonlinear, of the so-called shunting type, if people are familiar with this, or what we also more casually refer to as divisive normalization. And then if you do this, obviously, you start having interesting interactions between and across cortical columns. Again, I could spend a whole talk describing the myriad of interactions that we've identified. But just to give you a flavor for those, I'm just going to show you a particular kind of interactions when we present gradings, for instance, with different orientation in a center column and a far surrounding column. And so just to give you a preview of what I'm going to show you next, you're going to see neural population responses. So think of the x-axis as being neurons or preferred orientation, where here in this case, here would be 0 degree, maybe purely vertical. And then the height of the bar would be proportional to the response of the neuron with that preferred selectivity. So here, if you present a vertical bar in the center, you will find a whole neural population response kind of peaking at the center orientation and then kind of falling off around. The orientation here in the surround is tilted to the right. So we obtain a very qualitatively similar response. Again, this is a toy example, but I'll show you the simulation in a second, except that now because the surround is tilted slightly to the right, we see that the population response is shifted slightly to the right. Now, remember that we have this like-to-like pattern of horizontal connections between our center and surrounding columns. And combined with this nonlinear divisive type of inhibition, that means that this guy here in the surround, which has a higher response than this guy here in the surround, is really going to try to push this guy down. This guy here is also going to try to push this guy down, but maybe a little less because its own level of activity is less. But anyway, the point is that there's going to be potentially some very complex interactions between population of neurons in one columns and nearby columns. And depending on what we present in the center, in a reference column, and in the centering and in the surrounding, in the surround of that central position, we're going to have very complex interactions. So here's an example of an actual simulation. Oh, sorry, it looks like my movie is not playing. Okay, I don't know. I'm sorry about that. It looks like I'm having some trouble playing the video. This is Google Slide. Well, you'll have to trust me on that. What I was going to show you is an actual simulation of the dynamical system model when we present exactly this kind of center surround stimuli. When the orientation of the surround is tilted away from that of the center, you would have seen populations of neurons for the center and surrounds kind of going up and down and kind of working potentially here against one another, where in the end, the surrounding, the activity from the surround through inhibition ends up pushing away the center column. And so when we train a decoder to predict the orientation of the center, we find that we can essentially shift the perception of the neural, oracle decoder in the center based on what we put in the surround. And we found that in practice, this model was able to account for a host of contextual illusions. So the one that I just presented is a well-known one called the tilt illusion. Those things are, dependent on the spatial frequency, on the viewing distance. So it may or may not work, for individual viewers here, but, please trust me. These are standard kind of very well-known visual illusions. So the tilt illusion is interesting because when the surround is tilted just a little bit from the center, you should see here this vertical grading tilted a little bit to the left. So the surround kind of repels the center. past a critical angle, the effect reverses. If the angle, if the difference between the center and the surround increase past the threshold, then the surround starts attracting the center. And again, this may or may not work for you. And we found that this model was able to account qualitatively very well for this. And then when we switch the input neural populations, we can switch from orientation to color to motion, etc. We're able to show that the same exact circuit was able to account for a host of the so-called contextual illusions, including contextual illusions involving color, motion, etc., etc. So I'm going to run out of time, so I'm going to skip ahead. All of this is published, and I will encourage you to look at the paper if anybody is interested in the details. What I want to spend the last 10 minutes or so that I have is to tell you about, how it is now possible, how it's, how some of the more recent work we've done has been essentially trying to move away from this kind of more classical, continuous dynamics type of dynamical system models to leveraging modern tools from deep learning, gradient-based methods to really learn to optimize those circuits so that they can be embedded into deep neural network and trained to solve complex, visual tasks. And so, as I said earlier, one of the challenge dealing with, differential equations, as I'm sure many of you here know, is that it's or at least a few years ago, it was not really amenable to learning. And so all of the tweaking, all of the setting of the operations, whether you want linear, nonlinear operations, if you want particular pattern of synaptic weights, etc., all of that had to be tweaked by graduate student descent. Now, with all the bells and whistles that people have kind of discovered, working on modern day recurrent neural networks. I'm sure many of you have heard about LSTM, gated recurrent units. They have all these gates, and that really allows those discrete time approximation of this recurrent neural circuit to learn very efficiently, and in particular to be trained to solve very complex tasks. And so we've done essentially that. We've started from very popular recurrent neural network module called the gated recurrent unit, and we've used that to approximate our contextual circuits, approximating separate populations of excitatory and inhibitory neurons, taking into account this nonlinear divisive interactions and so on and so forth. And throughout the years, we've, starting from our relatively simple circuit of just horizontal connections, we've extended the approach to also incorporate with the same basic set of equations, top-down connections, so an ability to propagate information from higher level units onto lower level units. And then more recently, again, adding more and more complexity as the need arises when we try to solve more and more complex visual reasoning tasks. And then to evaluate the ability of modern deep neural network models, or I should say their inability to solve complex visual reasoning tasks, we've been developing an array of visual reasoning challenges. For the most part, they have been motivated by fairly standard cognitive psychology tasks. I'll show you a few examples, but that have been used to study human vision for decades now. And we've been able to adapt those simple human psychophysics tasks to kind of automated procedural generation, so that we could generate hundreds of thousands or millions of training data to really be able to evaluate modern day deep neural network architecture. So those are just representative tasks. I thought that I would spend most of my time telling you about one task that I think really highlights the benefit of feedback connections, recurrent connections relatively well. So we call this task the Pathfinder. So what you see here are, so on the top row here are positive, bottom row are negative examples. So you should see contours made of your paddles. And then on both the positive and negative examples, you should see two markers. I don't know if, again, depending on the resolution, there is one here and one here. So on the positive examples, the markers fall on the same contour. On the negative examples, they fall on two different contours. So think of this task as training system to find a path. And the question really is a binary one. Is there a path going from point A to point B? The learners have to discover that task from just positive and training examples. So we can parameterize, this task in a number of ways, changing the orientation, the distance of the paddles, etc. One particular parameterization we thought that would make the life of feed-forward neural network particularly hard is when we start making those contours longer and longer. And the reason for that is that, as I mentioned earlier, in a feed-forward neural network, the only way for units or neurons to communicate and incorporate increasingly more context or discovering increasingly long-range spatial dependencies is going, up, right? And by building increasingly large receptive field. And so the assumption here is that, we know that feed-forward neural network are universal approximators. They should, be able to solve the task if they are deep enough and if we give them enough training examples. And here we can generate tens of millions of those. But our prediction was that feed-forward neural network would need to have or to be able to build receptive field that encompass the entire contours, right, to be able to solve the task. And so the prediction was that the minimal depth required for a feed-forward neural network to solve the task should increase as we make the lengths of the contours longer and longer, if that makes sense. Because those feed-forward neural network build, receptive field size through depths. And so because they need larger and larger receptive fields, the minimum depths needed to solve, a longer and longer version of the task is that they should get deeper and deeper. I hope I was clear enough on that. In comparison, if you have a recurrent neural network with an ability to communicate, for units to communicate within a layer of processing, through local exchange of information, then in theory, a single layer of this recurrent network should be sufficient to solve the task. In fact, a very natural way to solve the task is what we call incremental grouping. All is needed is a unit to essentially discover one of the marker and then spread activity to the neighbor along the contour, and then incrementally spread activity until the end of the contour is reached. And then the question is, is there a marker or not at the end of that contour? And so here's our results. Sorry, let me try to move my Zoom if I'm blocking anybody's view. So this is a very complex plot. I'm not gonna go through all the details. I'll just say that every one of those cells, I'll draw your attention to the top row. I'll just say that if you look at individual cells, there should be 3 dots, each corresponding to the accuracy of a particular class of models for the 3 different lengths. So just to get it out of the way, we can take our recurrent neural network module, again, single layer, we can optimize it for the task, and it learns to solve the task for all 3 contour lengths. We can try to do this with standard convolutional neural network. They really struggle. We had good results with ResNets, which are much more efficient at learning. You can take a ResNet of any depth, and it can learn to solve the shorter version of the task, so pass length 6 and 9, shown here. But then as soon as you reach the 14 lengths, their accuracy essentially falls down to chance. You need to go all the way to 152 layers of processing for those neural network to be able to solve the task. So they really learn that through kind of brute force rather than through a much more generalizable and easily graspable strategy. We are replotting those results here in the lower left for the longer contour lengths. On the x-axis is the number of free parameter multiplier. The y-axis is the accuracy. We call it HGRU, as in horizontal gated recurrent unit. This is our recurrent neural network. It does perfect accuracy with the best sample efficiency. You can also get pretty good accuracy with feed-forward neural network, but it's going to take you orders of magnitude more training data. Okay. I'm running out of time, so I'm going to skip a whole bunch of stuff. Maybe just before I run out of time, just to convince you that this is not just a cute task that came out of the head of cognitive scientists. Interestingly, DeepMind a couple of years ago, back in 2020, developed a challenge for to evaluate modern transformer networks. So I hope most of you have heard about transformer networks. They have taken the field in natural language processing. They are taking over computer vision. I'm not going to tell you what they are, but they are really taking over AI. And so DeepMind researchers have created this challenge, which includes a number of tasks. They are not all visual, some are textual, etc. But they included our Pathfinder data challenge. And they try to train all the greatest and latest transformer architecture. And what you see here is that, this is not our work, this is DeepMind. They were not able to train any of the leading deep transformer network, even with 20 million training examples, to solve what would seem otherwise like a trivial task. This is just, binary images, black and white pixels, etc. That's what they call PathX. To be able to train the architecture on the task, they had to downsample very massively from 128 by 128 down to 32 by 32. At that resolution, they were able to train transformer networks, but the accuracy of these networks, they can be trained, but they're in the 70 something percent, when just a single layer of our recurrent neural network would solve the task perfect. All right, so I'm not going to have time to tell you much more. I'll just say that one question that I used to get is, if recurrent neural network, if feedback connections are so great, why is the state of the art in computer vision all feed-forward networks? We postulated that it had to do with the way those networks are trained. Recurrent neural network are trained, the standard way would be to use backpropagation through time. The challenge with those this training approach is that you have a linear increase in the memory cost as you want this network to allow them to have more and more time points for computing, because feed-forward neural networks already take up most of the memory available on the GPU. Then you don't really have enough time and enough power to really allow those dynamical systems to shine through a large number of computation through time. So we developed an extension of what is called contrastive recurrent backprop. I won't have time to give you the details, but the main benefit of this learning approach is that we can use regularization methods to force our recurrent neural network to have a steady state. And then, once we can force a steady state, we can use a steady state to backpropagate the gradient, not for every time point, but just for the final time points. And that works great. You can take that simple single layer recurrent neural network, slap it on a leading feed-forward neural network, and then train it through this method. And what you find is that you can really improve the state of the art in the domain of panoptic segmentation, which is closely related to semantic segmentation, if you haven't heard from it. We find that systems or feed-forward systems embedded, extended with those feedback connections can really start to make, it's not just a quantitative improvement, but we find qualitative improvements. Many of the false classifications are now suppressed through those horizontal feedback connections. You see the system here at work. So again, the segmentation here is not done through static processing stages, but really by allowing units to communicate and exchange information. We do not tell the neural network what to do. We just discover this, what looks like a filling in or incremental grouping strategy. It seems to start at the center of mass of an object and then spread activity until it hits the boundary of the object. Interestingly, it seems to be somewhat consistent with strategies leveraged by human and established by psychophysics method. We've extended the approach to incorporate feedback. One of the main benefits is that of sample complexity. And then more recently, we've extended to the time domain and the addition of attentional circuits, which have allowed us to do really well in the domain of object tracking in videos. In fact, we were able to lead the leaderboard for one of the main visual tracking challenge known as TrackingNet. I think we were #1 when we published the work. We're now #2. But anyway, I apologize for going a little bit over time. Hopefully we still have a little bit of questions time for questions. What I hope I've told you or introduced is a new breed of feedback networks, which are inspired by cortical circuits found in the visual cortex. I've shown you that, actually I skipped that, but I wish I had time to show you that we can get feed-forward neural network achieving the same level of accuracy as those feedback neural networks, but they need to get much deeper. They require much more training data. And when we do this, they do not exhibit the same sensitivity to contextual illusions as primates and humans in particular do. We've been able to push the state of the art, adding those feedback mechanisms on feed-forward architectures for contour detection, for panoptic segmentation, and for object tracking. And I'm sure I'm preaching the choir here. That's something that I've been trying to convince my computer vision colleagues is that I really think that computer vision initially and deep neural network were somewhat grounded in visual neuroscience. The two fields, and computer vision in particular, seem to have largely diverged, or it seems to be diverging away from neuroscience. And I think there is still an opportunity for us neuroscientists, cognitive scientists, to re-inject novel ideas for AI. Thank you so much for your attention.
Thanks for a very inspiring talk. We do have time for a couple of questions. In fact, one of them was asked in the middle of the talk, but it didn't have the heart to stop you. So the first question is from Heran. Thanks a lot. Coming from a computer science, he has two questions. First, with your square shape color experiment, did you try out spiking neural networks and see how they would perform? And two, what is a circuit model exactly? What each one of those triangular shapes represent? I think he's referring to the earlier parts of the talk.
Yeah, so, okay, let me just maybe to help provide some context, I'll share again. Yeah, so I think question refers to my duckling example here. Yeah. So I mean, what I'm showing here is obviously an idealization, but there's this data set called Sort of Clever, and so this is a standard data set in AI and computer vision, visual question answering, where there's something like, I think maybe a dozen shapes, triangles, squares, etc., different size. They can vary in size and aspect ratio and these kinds of things. And then they are given a color, again, so many colors, I don't know, half a dozen, a dozen. And so then, the systems are typically trained to answer questions about the scenes, like what's on the right of the triangle, what's on the left of the square, and so on and so forth. But the bottom line is that, of course, the architectures are always trained and tested on the same dictionary of shapes. And so my student just took this architecture, and then just try to train them on a simplified version, which is just the same different task. We now train them with pairs of shapes. Shapes can be in any position, different scale, etc. And positive example, compare pairs of the same shape and color. Negative example contains shapes that are different, and so the learners have to discover that from training data. So I hope that clarifies the second part of the question. With respect to the first part of the question, I don't think it's a matter of spike or no spike, or I think it's a matter of going beyond template matching. That I think if you take a CNN, whether it's spiking one or not, really what it does is a glorified template matching. I would go as far as saying this is a giant lookup table, and the bigger the better, apparently. And so I think what is needed for visual reasoning is something that is able to go beyond template matching, because if you haven't been trained, obviously you need to abstract away from shape, right? To demonstrate an ability to solve same different judgments, hopefully at some point the observer has to be able to solve the task for shapes never seen before. And obviously human observers can do that without any problem. I can show you an object that you've never seen before, two versions of it, or two different versions of two never seen before objects, and people will have no problem figuring out that they are the same different. What seems to happen in visual question answering is that the systems never really reach the level where they can exhibit this level of abstraction in ways that even ducklings can demonstrate. And so I don't think unless I'm there's something more about just spiking neural network that I'm missing, but to some extent it's less about whether you spike or not, and it's really much more about having an ability to in this case build more abstract representations than just raw global visual representations of the whole scene. And so the kinds of things we have in mind, and we've done collaboration with experimental groups, we've done EEG studies that validated this hypothesis. I think what is needed is an ability to, for instance, bind visual representations, neural representations to objects. And essentially you want the system to attend to one of those shapes, build a visual representation for that object, push that into working memory, then shift attention to the other object, extract a representation of that object, and then learn. Now the task becomes trivial. It becomes easy to learn the task. And in fact, we've shown that if we endow these kinds of ability to organize the scene perceptually, and what we did was very simple. We just took an image with those two shapes or multiple shapes, and split up the image into different channels, where each channel would contain a single object. So essentially, if you will, we solve the binding problem for the convolutional neural network because we allow it to process to process individual objects kind of independently. And if we do this, we find that the CNN can learn the task, almost, with very few training examples. So again, I think it's less about, spikes, no spikes, or better template matching. I think what this suggests is that, and perhaps what makes our visual system so robust and so sample efficient, is that we have an ability to organize the visual scene, which allows us in turn to build, higher level abstractions on top of visual representations that go beyond, the kinds of bag of word representations you'd be able to get with a convolutional neural network or equivalents.
I think there is time for another question. In fact, we have more than one. Perhaps you can then continue in the chat. But Moin is asking, thank you for the great talk. Have you examined the case of having branched contours or highly intersecting contours in the Pathfinder task? And how would the introduction of those how would it affect the accuracy of the recurrent neural network? Yeah,
that's a very good point. So nothing is published, but we've started to look into that. In fact, we are very interested in, we've been looking into neural ODEs as ways to train some of those recurrent neural network. It is a very good question because it is true that the complexity and the number of intersection along the contour is going to be actually a learning challenge. There's going to be a direct correspondence between so every time there is a crossing, the learning algorithm, I mean, there's an ambiguity in terms of how to allocate or how to associate the gradient to the correct path, essentially. And so you're right. The more intersection, the more problematic it gets. It is especially a problem for backprop through time. We found that our contrastive recurrent backprop deals better with it, but this is still going to lead to more errors. So that's a very good question. So I don't have much more concrete to respond, but that's a very good point. There's a correspondence between the credit assignment problem and this occluding contours during learning.
Thank you very much, Thomas. I think in the interest of time, I have to pass the baton to Etienne, who will lead the microtalk session. But thanks again for a fantastic talk.
Thank you. Thank you so much. Thank you, everyone.
Okay, thank you, Daniele. I'm sure that everyone needs to work for 2 minutes now. So I suggest 2-minute breaks. No more than 2 minutes, but at least 2 minutes. So see you in 2 minutes for the microtalk session.